Hello. Now that we have figured out the notions of a single pass of the radiation within the active medium and understood the ideas related to amplification and then the notion of threshold. So now let us look at the rate equations that govern the field inside the cavity, as well as we will add to that our understanding of the active material itself. So essentially at the end of this lecture, we will have the rate equations that are governing both the light and the populations related to the active medium inside the cavity. All right, so the Z propagating field I plus, so it was 1 over C dou by dou T plus dou by dou Z, and this was the operator that was operating on the field propagating along the positive direction, positive Z direction. And remember that we have the same set of approximations that the field is narrow band uh, at frequency nu and it is propagating along the positive z direction. So again, what I have is I have a cavity. The cavity is of length capital L. The gain medium, which is could be of a length which is small l, right? And the light propagating to the right is denoted at I plus. Light propagating backwards in the minus z direction is denoted by I. The one which is propagating forwards is denoted by I plus, and the one which is propagating backwards is denoted by I minus, right? And my this direction is essentially z. So this is my schematic, and similarly, if I want to write down the left propagating field, all that I need to do is reverse the sign of my z. So I have 1 over c dou by dou t minus dou by dou z. That is, I have changed z to minus z and I get I minus, and this is g nu, which is the same gain, but now this governs the radiation propagating in the minus z direction, I plus and I minus. When we have reflectivities of the mirrors, that is R1 and R2, right? When these two reflectivities are close to 1, in that situation, so you see that the radiation that comes out as the output, right, in that direction, for example, so the radiation that comes out of the output is only a small fraction of what is within the cavity, right? And this ensures that my I plus and I minus are actually quite comparable. So the field going to the right and the field going to the left, because of the large reflectivities of the mirror, are more or less identical. There is spatial uniformity and there is no gross variation between I plus and I minus, both as a function of z as well as between I plus and I minus, right? So we are assuming these two things, that is spatial uniformity and I plus is almost equal to I minus. We add up these two equations, right? Then I get the following form: 1 by c dou by dou t, and this is I plus plus I minus plus dou by dou z, and this is I plus minus of I minus, right? And on the right hand side, of course, you have the addition of the two fields, which is I plus plus I minus. I realize that both these fields are comparable, so this term essentially uh, actually is negligible, right? So I can ignore that, And what I do further is actually I integrate this equation. Let me call this equation number 1, and I integrate equation 1 across the cavity. And because I said that there is a spatial uniformity, which implies that I plus and I minus, both of these uh, do not vary with Z, right? Within a single pass, it hardly varies in Z. So if I integrate this across the length of the cavity, so on the left hand side, what I get is 1 over C. Now it is d by dt because I've integrated it over space. I have I plus I minus, and this field is more or less a constant in Z. So I get a multiplicative factor of L, right, which is the whole cavity. And then on the right hand side, I have G of nu, which is again uniform, times I plus I minus, both of these being uniform in Z, times small l now. That is because my G of nu integrated over 0 to L dl is such that it is G nu times small l, right? This is important to realize. So eventually the equation that I get is the following. It is d by dt I plus I minus equal to C times small l by capital L G of nu, right? So now clearly you see that this quantity I plus I minus gives me actually the total number of photons within the cavity. Let me call this as Q nu. These are the photons which are within the cavity. So I can write down that within the cavity, this is a rate equation that governs the growth of the photons in time within the cavity, and only accounts for half the story. The other half of the story is the outcoupling of the photons, right? So let us just look at that. So to add that feature of loss of the photons, so looking at now loss of photons, more importantly loss of cavity photons, let's figure out the rate at which the photons are being lost, right? So we know that the surviving photons, so I, the intensity, this is after round trip, let's say. This is basically R1, R2, right? The reflectivities at the two mirror times the intensity before round trip. This we know. That would mean that these are the surviving photons within the cavity, right? This implies that the fraction of photons lost per round trip is going to be simply 1 minus R1, R2. Not just that, what we require is a rate. We know that the total round trip time is simply twice the capital L by C. This is my total round trip time. Particularly, I'm looking at a gas medium where my velocity of light is c. So you see that my loss rate, photon loss rate, is simply the following. It is c by 2l, 1 minus r1, r2, right? This is the rate at which the photons are being lost due to outcoupling. I'm putting this back into equation number 2, and I get the final form of uh, the rate equation governing the photons within the cavity. So d by dt of q nu, q stands for the number of photons within the cavity, is going to be simply c l by small l by capital L times g of nu times q nu minus the loss rate, which is simply c by 2l, 1 minus r1, r2 times q nu, right? This governs the time dynamics of the photons within the cavity. My total rate of change of the photons within the cavity is related to the gain process and then the output coupling or the loss process. So, right now, if you recall, this the second term that we get is quite similar or exactly identical to the situation that we arrived through this discussion of threshold in the previous lecture. Indeed, I can rewrite this equation. For example, what governs the uh, I can rewrite this equation for for example the intensity, right? The governing intensity, it will be simply di by dt, which where di stands for now the total intensity, including the positive and the negative traveling paths, right? That will simply be where I'm just expanding g of nu. G of nu, is sigma of nu n2 minus n1. Put in the subscript nu to indicate that we are in the narrow band regime, and the second loss term, which is C by 2 capital L, 1 minus R1 R2 times I nu. Right? So this is essentially the rate equation for the field. So I just want to note a very important characteristics, that either we can talk about intensity, right? Or we can talk about the photon number, right? Or we can talk about the photon flux. These are all uh, quantities which are all related to each other. For example, my intensity is energy density times C. If I'm looking at photon number, right, I can think of it as being related to the energy density, for example. So, for example, h nu is the energy with respect to one photon. H nu times Q divided by the volume of the cavity is going to give me an energy density, right? Uh, Similarly, I know that the photon flux phi is simply energy density times C, right? And if I need to divide by energy, so this will give me photon flux. Uh, or in other words, I can as well write down flux as C times Q by the volume. Here V stands for the volume of the cavity, cavity volume. Or in other words, I can even relate my phi to intensity is simply I by, so phi can is also equal to I by h nu, right? So these are all equivalent. The other interesting thing I can, for example, if you look at the active atoms, so these are all different relationships which I wanted to keep in mind. We can write down equations equivalently for different aspects of the same thing. Um, we know that if I'm looking at the number density, that is my population, so Ni, number density of population in the state 1 or state 2, then if I multiply by the gain volume, right? Cavity volume is different from the gain volume, and this quantity is simply the number of atoms in the ith state, right? Because I'm multiplying number density with the volume. Similarly, you would also see that my V gain, that the volume gain volume divided by the total cavity volume, the cross-section area is identical for both of these, and hence this is simply the ratio small l over capital L, right? So just to keep these uh, things in mind, so that we can go back and forth between all these quantities, where Vg stands for the gain volume. So let me get to our final equations. Okay, these become our governing equations for the atom as well as the field. So imagine that my level 1 was the ground state, level 2 is the excited state, N1 is the number density of atoms in the ground state, N2 is the number density of atoms in the excited state. Then we can write down the following, that my dN1 over dt, like we had, It is simply the rate of decay from the state 1 that might go out of the system, right? Minus gamma 1 plus there is a increase in the, so I'm looking at various physical processes. So let me indicate that in a different color. So I have gamma 1 as the decay out of the system from there. Similarly, I have gamma 2, which is the decay from the excited state, and I have A21, which is the spontaneous emission decay. And similarly, I also, of course, have the field that is coupling the transition 1 and 2. So these are the decay rates associated with it. So my the ground state population is going to increase because of spontaneous emission. So there is a plus sign, and now there is A21, and this depends on the number of atoms in the excited state, which is A21 times N2. And then we can write down the usual sigma, right? Sigma nu times phi nu, which is my photon flux, times N2 minus N1, right? So what is this? These are the two terms. So for example, the negative sign sigma phi times N1 is actually the due to absorption, where we lose the number of atoms in the ground state because of absorption, and sigma phi times N2 is the which is arising out of stimulated emission. And just recall that this product between sigma times N2 minus N1 is precisely the gain G of nu, right? Similarly, I can write down my next equation, which is dN2 over dt, which is the change in the number density of atoms in the excited state. This is again minus gamma 2 N2. There is spontaneous emission decay, so there is loss due to spontaneous emission, which is minus A21 N2, which is exactly the opposite. And then you have the loss due to stimulated emission, right, which is sigma nu, which is giving you cross section. Phi nu is give the number of photons, and this is N2. And you have the increase in the number of the excited state atoms because of absorption. That is the other term. Uh, so right, we had already derived this. I am simply rewriting it uh, for the for putting it all in one place. And you realize that I'm going to add one more term here, and let me call that as something arising out of pumping rate. Remember that we cannot have a system of just two level atoms, and I'm calling this K as some pumping rate. How I get to uh, a larger value of N2 in comparison to N1, right, involves some other method or some other means of doing it, and that I'm capturing it all in this rate in this business called the pumping rate. The last rate equation is that of the photons in the cavity itself. So which as you know, is proportional to the number of photons. Is also proportional to the photon flux within the cavity. That is d phi nu by dt is simply small l by capital L, and this one is g nu. Again, I will open it up. So sigma nu n2 minus n1 times phi nu. This is the term arising out of change of the photon flux due to stimulated emission and absorption. And you have the loss rate, which is governing the outcoupling of the cavity photons as the lasing output itself, which is C by 2L, 1 minus R1 R2 times phi. So these three are my governing equations that basically looks at rate of change within the cavity. Remember that this is serious approximation. We are not worried about the notions of pumping yet. We have restricted our atomic description to just N1 and N2. we have not essentially, looked at the spatial dependence of any of these quantities. We are saying that we might have a situation where the uh, gain atoms, the active media is of course uniformly distributed across the cavity, hence they do not have any Z dependence, but that doesn't absolve us from not considering, the Z dependence of the photon of the field distribution. But at the moment, we are ignoring that, we are integrated that out. So what we have is basically just the number of photons or the photon flux within the cavity without worrying about its spatial dependence. Right, so these are the three equations that are going to govern our dynamics of the laser, and clearly you will see that these are nonlinear equations. Simply because we have these products which are governing, you have this phi times n2 minus n1, which is a strong uh, nonlinearity which is present in through all these equations, and this nonlinearity makes it very difficult to obtain a general solution for such equations. Mm, so I can go a step ahead and rewrite, using these relations which I have pointed out here. I can actually rewrite these three equations in a slightly different form, where rather than looking at number densities, right, one is looking at numbers. So we are looking at photon number rather than looking at photon flux. We are looking at uh, number number of atoms in the excited state or in the ground state, rather than looking at number densities of atoms in the excited or the ground state. And here we will utilize these to obtain the following. That is, my phi nu can be written as C times Q nu, which is the number of photons in the cavity, divided by the volume of the cavity. Right? You can just get this self-consistent with my above definitions. Um, and our Ni is the number of atoms in the particular state, is simply the number density of atoms in that state multiplied by the Vg, which is the uh, volume of the gain medium. So putting these two things together, I can write down the following same three equations later down in these variables. For example, dn1 over dt will be simply the total number of atoms in the ground state, and this is simply minus gamma times gamma 1 times n1 plus a21, which is spontaneous emission rate, times n2 plus, now you see that replacing c by that, and I am replacing my, so you will get capital N's are replaced by uh, small n by Vg, so you will get a ratio of Vg over Vl here, which is same as small l over capital L. So what you get is C times small l over capital L, G of nu, right, which is sigma times n2 minus n1 uh, times Q nu, right. uh, Similarly, my dn2 over dt is minus gamma 2 times n2 minus a21 times n2 minus c small l by capital L, g of nu q nu plus p, and I'm defining p as simply the pump rate k multiplied by the volume of the gain cavity is give me the total amount of pumping that is required. That is what is my p here. And then I have the last equation, which is now governing the number of photons within the cavity, dq nu by dt. This is the cavity photons which are in the lasing mode, right? This is c small l by capital L, g of nu q nu minus c by 2l, which is 1 minus r1 r2 times q nu. So in this equation, remember that g of nu is simply sigma times n2 minus n1, right? Which is the number of atoms here. This definition is only true for our this set of equations, right? This symbol. All right. So why I have done this is basically to drive home a particular point, which is let me look at what is the total number of excitations, right? If I just consider atoms and there are no fields, all the atoms will be in the ground state. There is nothing more to talk about. But the moment I put in, these lasing photons and there is a dynamics going on, I can ask what is the total number of excitations and how do these excitations change with time. So what I'm doing is basically adding up this two equations, which is the excited state population and the total number of cavity lasing photons within the cavity. So I can see that this is related to the following. My d by dt of N2 plus the cavity photons. These are, this is what is being generated, and this is the excitation that I have. It depends, you add up these two and you will find the following. It is minus gamma 2 plus A21 times N2. The generation and absorption, that is the generation of the photons due to spontaneous emission, right? And the loss of atoms in the excited state, these two terms will, precisely cancel out. All right, when you add up these two, they are they are generating each other in a sense. So plus, so the term remains as the pumping itself, and the loss, which is C by 2L, 1 minus R1 R2 times Q nu. So you see that the total number of excitations, this can be interpreted quite nicely. This is my total number of excitations. And this is basically the excitations are lost. For example, the atomic excitations are lost due to inelastic processes, right? Inelastic loss and spontaneous emission. The total number of excitations increase because of pumping. This is my external pumping that is driving the population, and the excitations are lost because the photons which are generated, the cavity photons are getting as my lasing output, right? Lasing output itself, that itself takes away the excitations which are generated within the cavity, right? So this is essentially what is happening, and there is an exchange between the light and the atom. What you are actually putting in is pumping, and you are extracting variety of stuff out. The excitations are not only lost in generating the lasing output, but they are also lost because of spontaneous emission, and inelastic losses that they might be. So everything doesn't get converted into useful lasing photons.